All right, everyone, as I sit here and enjoy my sugar-free Reese cup, I hope that you are enjoying my lecture videos. Well, you probably aren't, but at least I hope that you're taking something away from the lecture videos and that you're learning some great and new information that you can apply to your future job. That's why we're taking the class, right? So, we just finished with section 3 of a EPA method, and we decided to use EPA because it makes a great learning opportunity because they do wonderful detail within their methods. And we just finished the definition section, which I said was really one of the most important sections that we would focus on for this particular lecture series. And it was a lot of definitions, it was a lot of standard discussion, quality discussion, how are we double checking everything built within the method. That was the purpose of section number 3. So from here on out, we're just going to do a very brief introduction with each one of these sections that we're going to see in a proper method, or that we could see in a proper method, talk about why they're there, talk about what the purpose of them. And the first one that we're going to talk about in this video is going to be this section called interferences. All right. So interferences first, I want you to understand that not everything has interferences, okay? So there are methods that are out there that we just really don't see an interference of, and I'll talk about what really a proper interference is in just a minute. But there are certain methods that when we go into this section, it will say none, or it will say not available, information not provided. Something is happening here within the method that we are not really getting weird or wonky data from an instrument or a procedure or a lab method. So first and foremost, not everything has interferences, but quite a many things do. And it's just because the idea of a sample is complicated. So the more complicated the sample is, the more prone that we are to interferences within that particular method. All right, so what is an interference? Well, most of the time we have an expected concentration that we should see from these values, right? So in section 3, we just talked about all of these standards that we are putting into place to double check everyone's work. The field collector's work, the laboratory work, the instrumentation work, the standard deviation, both in the field and within the laboratory. I mean, it's one thing after another, after another, after another. However, when we do some of these data reports and we look at some of these concentrations that are showing up on those data reports, very often the expected concentration is not matching. All right. So there is a chance, though, that the number, the value that's showing up here, it's not really my fault. Okay. And it's not really your fault, because the sample could actually have some things in the matrix. The sample could be bringing something to the table that is interfering with the signal that we are getting from our procedure, our instrument, or whatever we're doing this lab method on. And that's what this section is all about. It's about these interferences that are normally happening in a run-of-the-mill daily process, right? With a regular type of sample that we would see that would follow this method. And maybe how can we fix it in order to make this process a little bit better? All right, so section number 4 is all about these interferences. And I'm just going to take a few minutes here and just kind of read some blurbs. It says, during the analysis, major contaminant sources are volatile materials in the laboratory itself and the impurities in the purging gas. So this is letting me know, listen, if I do this lab method in-house, then there is a chance that if I'm in the lab and there's other people in the lab doing other things, these other volatile materials that might be present, they are going to show up or possibly show up and weird out my data or my reports. So this is almost a way to say, make sure you're not doing anything else in the lab, or have a dedicated area where you're doing the sample prep, so that way you don't cross-contaminate or interfere with the signal. It also says that the purging gas, whatever that is, could also provide us some contamination. It could provide us some interferences. It could help our expected concentration not match what we're getting in the laboratory and interfere with that process. So these are just ways to say, heads up, when you do this method, this is what you need to look out for. And that's the purpose of Section 4 interferences. It also says the use of Teflon tubing, Teflon thread sealants, or flow controllers with rubber components in the purging device should be avoided, since such materials outgas organic compounds, which will be concentrated in the trap. So even pieces and parts of our equipment are going to cause us a problem. When potential interfering peaks are noted in blanks, the analyst should change the purge gas source. So this also is letting me know, listen, this is how we take care of it. So it not only provides us the interferences, but it also helps us to determine what we need to do for a solution. How can we prevent this from going on? What can we do to make our values a little bit better? It also says subtract the blank values from the sample results. That is not permitted. So you cannot do that to fix the data or to make it work with what you need to work with. The interference section continues on into the next page. Interfering contamination may occur when a sample containing really low concentrations of the compounds is analyzed immediately after a sample containing relatively high concentrations. So what you're going to find here is that in a laboratory, we don't really have any way to know what this sample is going to be bringing to the table. If it's a true sample, and if it's a sample with an unknown concentration that we're trying to find, like how much is actually there, we can't really rank them in order to low to high. And that's because we just simply don't know anything about the samples. Now, with our standards, we can do that with our standards without a problem, right? So our standards that we used in a laboratory, we know what those are. We've mated those. We've put those in there. I can analyze those from low to high if that's what's going to be needed here, and very often that's exactly what's done. So for instance, when I go and make my cal standards, I'm going to make my cal standards, and most of the time I go with my lowest concentration to the highest concentration for this particular reason. Sometimes the high standards make it a little too dirty, and not everything is flushed out, not everything is cleaned, and by the time low concentrations come in, they are contaminated in a way by what has happened and ran in a previous run. So here is the method's way of saying this can also happen to samples as well. If you know something about the samples, please run them in that particular order, but a lot of times we just don't know. We're just taking run-of-the-mill, putting them in, loading them up the way that we want to load them up, and see what we get there at the very end. A preventive technique is between sample rinsing. So this is very often the case. If we are working in really, really low concentrations, we do see putting what we would call blanks in between the samples as well. And the blank just helps the instrument have enough time to rinse itself out, clean itself out before the next sample gets injected. So it's one of those tricks that we use in a laboratory, and that's why sample rinsing, aka rinse some blanks in between your samples, is often a thing in a working laboratory. Next up, 4.3, special precautions must be taken to determine methylene chloride. So apparently this is a component that is going to be causing some interferences. We need to pay special attention to this thing, and the interference section is going to go through and tell us how to handle that. So again, interferences can be general terms, general usage, this overall idea that things can interfere, and this is how we limit the interference. Or this section can also specifically target a few components or maybe just one component and say this is an interference, and if this is what's present, then this is the way that we fix this. This is the way we make this method a little bit better. 4.4, you see that again, and it says traces of ketones and methylene chloride and some other organic solvents here can present even in the highest purity methanol. So this is another source of contamination, and we should make sure that we pay attention to this before we prep our standards and before we put methanol into every single thing across the board. So the idea of solvent purity is also a thing. So purity is going to be very important, especially for solvents. What you will often find in a working laboratory, the solvents, the purity is always a problem, and we want ACS grade whenever we can. So ACS grade is often the cleanest, it's often the purest, it's often the best quality of solvent or reagent that we have out there, and that is what we go for every single time, as long as it's not outrageously expensive. Now, there are other grades of reagents that are out there. We've got USP grades, we've got lab grades, we've got reagent grades, we've got biochemical grades. We just have tons of different names that get assigned to the proper type of solvent that we're using, and it's all about purity. That's all that it is. So ACS grade is typically the go-to almost every single time in a lab environment for a chemical or reagent that we order. All right, so that's section 4, interferences. Again, not everything has interferences, but quite a bit of stuff that we do in a laboratory does. So this is what to watch out for, and this is how to fix those problems if they show up. Section number 5 is going to be dedicated to safety. As you can imagine, if this is my first time doing the method, like, I would have no clue what I'm doing. Oh my God, I'm going to blow myself up. So safety will give me this idea of how to handle myself and how to handle the reagents and what I need to do on my end to make sure that nothing is going to happen to a person as they perform this method. So a very good resource for you to use if this is your very first time doing the method. And this is also going to be built in to the proper SOP, just like interferences will be. They will be built into the SOP if we can prevent those from happening. But it says safety for this particular method. Number 1, the toxicity or carcinogenicity of chemicals used in this method has not been precisely defined. So you're going to do this, but guess what? We don't really know if it's really going to be cancer causing or not. Each chemical should be treated as a potential health hazard and minimize your exposure to them. Section 5.2, the following method analytes have been tentatively classified or known as human or mammalian carcinogens: benzene, carbon tet, 1,4-dichlorobenzene, 1,2-dichloroethane. All of these are particular components that we would be analyzing for if we followed this method. So what this is saying is that, hey, if you're going to be doing this stuff, you probably have standards. If you have standards, these are going to be high alert because you need to handle them with proper care. If you are analyzing samples that have these components in them, there's chances that those components in those samples, and maybe those samples in themselves, can cause harm to you with your health as just a regular old person in the lab working on it and prepping it and doing whatever. So handle it with care, and that's the purpose of the section on safety. All right. Next up are equipment and supplies. This is going to tell me kind of the stuff that I need lab-wise in order to make sure that this method goes through the proper way. Now, keep in mind that equipment and supplies does not say reagents. So very often this will have its own dedicated section here, and the only thing that will be highlighted in this equipment and supply will be exactly equipment and supplies. So everything from glassware to filter paper to tools that I need in a laboratory environment, including the equipment pieces, are going to be found in this section. So for instance, if I wanted to adapt this method in our laboratory space, it looks like I need some sample containers. Now, look at what it tells me about sample containers. 40 to 120 milliliter screw cap vials, each equipped with a Teflon-faced silicone septum. Guys, I need you to understand that in equipment and supplies, if we are not following this exactly, or as close as we can get it, then we violate the method. So for instance, if I did not use a screw cap vial, but I used something else, I could be in violation of the method. So this is an area that is very important. It's overlooked, quite honestly, but there are immense number of details that's in this section that pertain to us as laboratory workers, because there's a reason that they put screw cap vials in here. Because there's other types of vials that I could choose from. There's other things that we can use. And because they specifically said screw cap, then there's a reason for that. And I want to make sure that I match this process as close as possible. If not, I'm in violation of the method. And it says prior to use, you're going to wash all the vials in septa with detergent, and you're going to rinse it with tap water and distilled water. Allow the vials in septa to dry on kind of air dry at room temperature, and then place them in a 105-degree oven for 1 hour, and then remove and allow them to cool in an area known free of organic compounds. So this is the method's way of telling me that in my SOP, I should have a SOP written for cleaning of the vials. This is a whole thing in itself, right? So for this particular lab worker, I might be like, okay, you are going to be dedicated on sample processing, but you are going to be dedicated on cleaning and preparing all of our glassware that we're going to be needing for this particular method. That's what your role is going to be today. And I would give them an SOP. And the SOP would include the cleaning parts of everything that needs to be used, everything that needs to be done. Sterilization, cleaning, washing, drying, you name it, this is where this is going to be found. And that's how those SOPs are built. So as I scroll down through the equipment and supplies, it says a purge and trap system. So this is a piece of equipment, and it says the purge and trap typically consists of 3 areas: a purge, a trap, go figure, a purge and trap, and something called a desorber. And it says there are systems that are out there that will do all of this in one. It's typically under one cover. We have one of them in our lab spaces. And then under 6.2, you're going to find individual steps that are related to the purge and trap system. Notice it talks about the dimensions of the purge and trap system. It talks about what it should be doing, what it should be made of. Again, it gives me very specific details. And that also means that companies that are out there making purge and trap systems, they are going to be made probably across the board the same way by different manufacturers. And the reason is because these manufacturers know the requirements of why someone would need their instrument in the first place. So if they use those requirements in the proper approved methods by the government, in this case the EPA, they're going to make sure that their instrument meets this criteria. So that way they can legally sell their instrumentation to a laboratory, so that way labs can use them across the United States. So notice it goes through a lot of different details of that particular piece of equipment. Again, the purpose here is not to talk about these pieces of equipment. It's just an overall review of what a method actually is. All right. 6.3 is also another piece of equipment that we need for this method, and it says a gas chromatography. We abbreviate this as GC. A mass spectrometer, so we abbreviate that as a MS. So we need a GC-MS system, and just like before, this is section 6.3, and there are a couple of pieces of criteria that fall under this category, letting me know what my GC-MS should be able to do. So for instance, it says the GC must be capable of temperature programming and should be equipped with a variable constant differential flow controller so that the column flow rate will remain constant throughout a desorption and temperature program operation. If the column is to be cooled to 10 degrees or lower, a subambient oven controller will likely be required. If syringe injections of 4-bromofluorobenzene will be used, a splitless injection port is going to be required. All right, so again, it's devil in the details. It tells me full blank, all out, this is what you need, this is how you need to do it, this is what are the minimum requirements that you're going to have to meet in order to do and implement this lab procedure in your own testing laboratories. All right, so 6.3 is still GCMS, 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 GCMS. 6.4 are syringes and syringe valves. So it talks a little bit about the syringes, which is going to be doing the injection of the sample into the instrument. It'll also be, again, syringes that you are using throughout the lab procedure could be located here as well. Notice it even says gas tight with shutoff valves. So those are going to be a thing that we're going to have to need for this particular experiment in some form or fashion. Why? The lab procedure tells me that. But again, that's the purpose of this section of equipment and supplies. After this section, we then go into reagents and standards. And when we get into the reagent and standard section, this is where all of our chemical solutions are going to be detailed. So for instance, it says methanol is a reagent that's going to be used, and we want to demonstrate that it's free of analytes. And the reason is because they specifically refer to that in the interference section of your method when we talked about that and highlighted that just a few minutes ago. But as I scroll through the reagents, it's going to tell me all of this kind of stuff. It's going to be like, hey, section 7.2.5, that is a reagent that you need. This is ascorbic acid. I want you to use ACS reagent grade granular in order to do this method. If it's not ACS grade, you can't use it. It's got to be ACS quality or higher, but ACS quality is typically the highest of the highest as far as purity goes. Granular, well, there could be different mesh grades. There could be different, versions of powders or grains or solids, big chunks, little chunks that I could get in ascorbic acid. And it gives me a keyword that I need to use in order to search for ascorbic acid in a online third-party reagent supplier like Fisher, VWR, and so forth. Next up is 7.3, and it says stock standards. We know what those are because those are from the definition section of the method. So SSS, these solutions may be purchased as certified or prepared from pure standards if you use one of the following procedures. So if you don't want to take the time-saving approach of ordering it and purchasing it as certified material, then you can make your own. If you make your own, this is how you do it. This is what you need to use, blah, 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 blah. 7.4 is primary dilution standards. We talked about that too. That's in the method definition section. It's one of the reasons that we talked about it, one of the reasons that we spent time on it. So PDS. And primary dilution, it's going to say this is what you need to do, this is how you need to make it, this is what's going to go on. So they really, again, tell you verbatim what you should be doing in a laboratory and build that in to your SOP. 7.5, fortification solutions for internal standards and surrogates. That was also in the definition section. We now know what fortification means. I add it. I know how much I've added. I want my signal to go up. So it gives me details about how to do the fortification. A solution containing the internal standard and the surrogate compounds is required to prepare laboratory reagent blanks, also used as a laboratory performance check, and to fortify each sample. Prepare a fortification solution containing fluorobenzene, internal standard, 1,2-dichlorobenzene D4, surrogate, and BFB, surrogate, in methanol at concentrations of blah, 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 blah. So again, directions are here. It would be my job as a lab manager to take this information, break it down, so that way people can follow these directions and really follow through with what the method requirements are going to be. 7.6, preparation of lab reagent blank. 7.7, preparation of lab fortified blank. 7.8, preparation of calibration standards. And then finally, we get to section 8. So that's where I'm going to stop this video. And I hope now you're beginning to get a larger, broader picture of what a method is doing for us. Not only is it giving us procedure details, but it is straight up telling us how to make some of these solutions, many of them actually, in a laboratory method. So I would take these paragraphs, I would break them down, I would make sure that these are incorporated in a SOP in some form or fashion, and make sure that they are represented there. So that way our lab workers are following straight up directions. They don't have to think about it. They don't have to do any math. They don't have to do anything like that. Just follow the directions and you will be able to bake your cake, and you'll be able to produce data from the method. All right, so in the next video, we're going to continue on here. This is going to be section 8 for sample collection, and we're probably going to scroll on through some of the other sections fairly quickly, so that way we can end this method talk and move on to something else, which is called an SOP.